Alright, so I think we are live yesterday, or actually not yesterday, about 8 days ago, unfortunately. Yeah, that's a lot of time. I streamed a previous part to this particular episode in which we designed a suborbital rocket, and that particular rocket had some parts yet to do, uh, which was completed by me later. But after I guess 8th of August, I was not able to actually find time to practice KRPC. But yes, today here we are, and I'll try to be consistent from here forward. It's just that was a little busy, but yeah, that's not what matters at the moment. We should continue with the suborbital rocket. Over here, let us move to the code as well. The code is on this display, which I have not yet switched. Okay, cool. So this is the lesson number 1 that we are working on at the moment, if I'm not wrong. All right. All right, all right, all right. Audio is good. Audio is good. So yes, this was the code which we were using. I'll like to switch this to another tab so that things are much better presentation wise. Okay. The thing that we did previously was basically, I guess, try to deploy parachutes, and let's switch to the rocket center. We used Ariane 5 as a rocket. Okay. Thing is, it did not work that well. I mean, in certain areas it was working well, but the entire implementation was not that, I'll say, flawless. So I added a re-entry module over here like this. It did manage to re-enter. So what I'll do is I'll very quickly go through the initial previous code, run it, see how it works, and after that maybe I'll do another suborbital mission, or else we'll go to the next lesson, which is an orbital flight. So I'll launch this guy. And we'll have to wait for a while then. Okay, so that's ready. Here it is. Here's the code for the rocket, and I think we should start running it one block after the other. So I'll prefer streaming the rocket instead of the code, because the code has been previously discussed by us, right? Server has not been connected yet. This should make a connection. The second code block, it got executed, so I guess yes, we have a connection over here. We can see suborbital flight. This is the third one. This is a combined code. I'm not sure if it's visible. Should be visible now. This is basically the code, the entire block. This, first of all, let me go through it. It checks for the altitude. Once the altitude increases, like is greater than 10,000, it does the gravity turn. Once that's happened, the solid fuel is separated based on the amount. So when the amount is less than 30, detachment happens. After that, we check for liquid fuel. Over here, liquid fuel of 800 is not enough. So like once it is once the liquid fuel is at 800, we can assume that the liquid oxygen is also not enough to run the rocket. So it switches off that particular engine. There's an engine separation which happens, and the next stage is started. So the throttle is set to 0 and again started, because engine separation needs to be smooth. After that, we move for the apoapsis. We go for about 600 kilometers of altitude. The thing is that over here we are going actually quite up, because this is a powerful rocket, and what is happening because of that is we are facing some problems while re-entering, which is why there have been some improvisations to the, I'll say, re-entry module. And after that, what happens is we activate the stability assist system, and we move to retrograde. So the rocket enters retrograde so that it can use its heat shield to in a way protect the inner components. After that, the surface altitude of about 100 kilometers is where we reignite these engines to trim as much of a velocity as possible, and say at about 2000 meters we deploy our fairings and we attempt a landing. So that's about this particular code. So once I run it in a 5 seconds, it will start over there. So I'll switch to the rocket preview itself so that it's much better to understand, and I'll run this particular code block. So I think we should have a launch anytime now. There we go, we have a launch, and uh, here's to hoping that everything goes as we wrote in the code. I think it's pretty obvious that it will work as expected. But I today want to go to an orbital, I'll say, lesson. uh, Before that, I'll like to learn more about the control mechanics or directions, etc. Because previously I did face a little bit of a difficulty in configuring the, say, autopilot and the stability assist system. So I'll first like to know it, and also it's a little tricky, not exactly very difficult, but a little tricky on to make sure that we are using the right parameters. So sometimes, so there are there are three reference frames. There is a surface reference frame, there's a orbital reference frame, and if you reach a particular orbit, then there's another reference frame as well, like with respect to a target as well. What happens because of this is that a lot of times we end up referring the wrong parameters according to the situation, which results into not so good results in terms of, I'll say, what we intend to do. So a surface based velocity parameter might not be a right parameter to refer to when we are orbiting, right? So, and there's always going to be a difference of, say, a particular delta v based on the rotational speed of earth. So there's that, right? And yes, now our altitude at the moment is at, say, 50-60 kilometers, and our apoapsis is 200 kilometers strong and growing consistently. But the thing is, we are forming a very sharp ellipsoid, so which is why we enter so fast. We work very similar to an ICBM, just it's that this ICBM is pointed at the same country from which it left, so that's even worse. Okay, so we have a stage separation. We have added some time delay over here as well, so that these don't blast off into each other. That's not cool to see. All right, what happened? Okay, we reached the apoapsis of 600 kilometers, and yes, now we have moved to retrograde already. So I'll time warp a little bit to again come at a altitude of 100 kilometers once we reach the apoapsis. So after reaching the apoapsis, we'll return back. So a little bit before that, I'm supposed to switch off the time warping, because, well, time warping will do a simple thing, and that is basically not allow us to return back to what I'll call as the retrograde orientation. So once I stop the time warp is only when it will be able to return to a retrograde position. And it's not that steep, I'll say. It should also not be too shallow, because if it is too shallow, the re-entry is too shallow, then we'll basically be in the most dense atmosphere zone for a lot of time, and it's definitely easy for the rocket to then hit up. By the way, the thing is that during this particular re-entry phase, what seems to be happening is that our engine is burning down. So maybe what I can do as a change is change the rocket design so as to bring the heat shield below the fairing, and after that we'll detach this guy, that is the liquid engines, and so the heat shield will actually do the job that it is supposed to. So over here at, say, around 100 kilometers, we have started reducing our altitude, which is good. and now we are simply supposed to reduce as much of a velocity as possible. All right, bleed off as much of it as possible, so that we make it back nicely, right? Okay, so this is where the re-entry begins at, let's say, 40 kilometers, like the most heated part of it. The engine is able to manage quite a lot of it though, so the deceleration happens very quickly because of a literally active second stage trying to, reduce the velocity. This also has some problems, as in we definitely increase our time in this, I'll say, very dense atmosphere, but it turns out we survive with the engine as well. Just cool stuff. It's just that we are waiting for an engine deployment yet. We're trying for a retrograde very hard, and the velocity is very much in control, I'll say. And at 2000 kilometers, 2000 meters or so, I'll say we should have a deployment, and yes, we do. Only problem is that we are not able to deploy this guy. So what happens is we are not slow enough to slow down completely. So I think because of that we are hard landing in the ocean. See, okay, the crew survived for sure, but we lost the rest of it. So if we could have discarded the other parts, we could have done this, but I think this is pretty optimized. This is working quite well. So I'll switch back to the code, and now we will try for a second lesson. I'll call it lesson 2, obviously. Lesson 2 will be based on the second lesson of KRPC. So I'll go to KRPC. And we'll see what lesson 2 actually is about. So here we go in Python. Yeah, tutorials and examples. Okay, second lesson is suborbital, or I'll say reference frames. And okay, we use a left-handed coordinate system over here. Position of origin, okay, as denoted by the x, y, and z coordinate. Okay, so the origin with respect to the surface is the center of the planet, which is cool. And that is obviously should be the true reference point in this particular situation, while we are in say in an orbit along Kerbal, or while we are in like a trajectory along Kerbal. Once we say enter another object, or the sphere of influence of another object, or the gravity well of another object, we should refer that particular reference frame. So based on that, I'll go through this particular document, because even I have not gone through the entirety of it yet. Okay, let's see the Python version. First we make some connections. Then we'll decide the orbital frame. Okay, okay, so we print the current position of the object. Okay, floating integer, like floating number, vessel.orbit.body dot reference underscore frame. So I'll have to check out what this does. Okay, so turns out once we are in orbit, the reference frame changes. The reference frame now switches to the center of mass, I guess, of that particular object. Okay, orbital reference frame. Alright, so there's a vessel reference frame and there's a surface reference frame, and similarly there's an orbital reference frame. Okay. uh, there's a vessel reference frame, surface reference frame. Okay, so these are the reference frames. So I guess these will be very useful while docking, so that the relative velocity between two moving objects at two different orbits can be determined to make corrections. I guess there's particular this docking port reference frame as well. So we can set a particular docking frame as a target, docking port as a target rather, and then we can go towards that particular docking port, right? So we can create some custom reference frames as well. Yeah, that's good. Okay, we can convert positions, direction, rotations and velocities between different reference frames. Okay, visual debugging. Current one is a challenge. Okay. All right. So this draws some cool ass arrows. I'm not sure where those will be drawn, but I'll have to check this out now. Okay, and this demonstrates the use of reference frame. Okay, so we can now, based on this, make the vessel point in various directions. So let's check it out. We establish a connection, we activate the autopilot, then we decide that the reference frame should be with respect to the surface. All right, then we activate the autopilot, then we set the target direction. Okay, and we wait. Cool. Okay, okay, so this is with respect to the nav ball. Now the thing about this is that these are constant values. So if I am to say do a gravity turn, I can definitely use these, but these cannot be used in a very linear, very smooth increase. So for example, if you want to gradually increase the degree of turn, I don't think you can directly use like the target direction. Sure, we can use a particular integer over here, or a number over here, and then we can make that, change that number based upon the altitude, if you are to directly use it. But there's another better option, which is, say, that's what we did in the re-entry, right? So during the re-entry phase, we actually activated the stability assist system and we went retrograde, and that meant that worked well. So I think that is a better approach, but definitely learning this is not bad. Cool. Then there's orbital directions. Okay, so we can make the vessel point in various orbital directions, and this is in the orbit mode, so it uses orbital reference frame. Cool. So again, we change the target direction based upon the orbital reference frame. Yeah, pretty obvious. Okay, now we are talking about prograde. So this is how we can point the vessel in a prograde direction. Okay, with respect to the surface mode, so I guess we activate the vessel, then we switch the reference frame to surface velocity. Okay, and then we target to 0 and 0. Okay, so what did we do here? Okay. Vessel speed. So we have defined two different reference frames here, and we are calling for the speed with respect to both of these, and we are printing those out. Cool. Here again, we have used the orbital reference frame and the surface reference frame. And then we are printing those out. Okay, this is interesting. Here we are counting or calculating the angle between the direction the vessel is supposed to point in and the direction the vessel is moving. Okay. So how do we determine the angle, like the direction it is supposed to be pointing in? Will it be determined by the say prograde, retrograde, such commands, or we can custom define it as well? So let's find that out. D is the direction, and V is the velocity. Okay, so a dot product is okay. So we have a dot product between two vectors D and V with 3 dimensions, and then we calculate a magnitude. Okay, so we use the math library, calculate a square root basically, and say our initial angle is maybe 0. So if the dot product is greater than 0, okay, it will be the angle is cos of dot product by V mag, which V mag is the magnitude of the velocity. Okay, so the net velocity, that is. And okay, and dot product over here is build the dot product and do 180 into pi, cool, into 180 by pi. So this is the, I'll say, formula to calculate our angle. And then I'm not sure why I sleep for a second. Alright, now next is landing site. Now this should be useful. So I had this plan of using the suborbital rocket as a ICBM kind of design, wherein we can do a return to home automatic Falcon 9 style landing, and turns out we can provide our base coordinates as well. So let's check this out. We have a body, and then we determine the landing latitude and the landing longitude. Okay, so these are the x and y coordinates on the surface of the Kerbal planet. Okay, we have an altitude parameter as well. That's so cool, man. So landing position is landing altitude comma latitude, so I mean longitude and latitude with respect to the body reference frame, considering that the altitude should be 0. So q long is sine of landing longitude by 0.5 by pi by, this should be some formulas to maybe get to these conclusions. So now landing reference frame is okay with respect to the body reference frame. Okay, I'm not sure what do they mean by drawing these lines. Are these lines drawn on the vessel or something? I'm not exactly sure. The best way to try that out is probably by launching a, I'll say, fighter jet itself, because it will be able to do some good maneuvers, right? So I'll switch to the Kerbal gameplay and we will revert the project, or we can go to the first of all, we can recover the vessel. So that means we get some experience for our astronaut as well, which is cool. And once that's done, we can now go to the spaceplane hangar and load a particular craft. I'll most probably go with something which is fast and maneuverable. So Dove is good. Dove is not exactly fast. Osprey is good in terms of speed as well, and very aerodynamic. Afterburners, or what they call air breathers, right? So I'll launch this guy. I think this has a single crew capacity, so not much of a thing, but interesting in terms of learning. So okay, we'll start the server By the way, we are launching from the second runway over here. This is much farther from the original space station, so we are somewhere over here, much more remote from the original launch pad, which is not even sure where it is now. Yes, there it is. It is somewhere there. Yeah, cool. That's not a problem. So first of all, I'll take this. I'll stop the server and I'll move to the code 2. So over here, I'll save this and we'll start another code, another notebook for that matter. This one is going to be lesson number 2. Alright, I'll fill in them some repeatables. So first let's import the libraries. This time we are going to need math as well. Cool. Activate current vessel is the thing, right? No, connection. Okay, vessel. Okay, first of all, connection is used to connect, so it's KRPC dot connect. We'll name it as reference frames, right? So we'll name a vessel as connection dot space center dot active vessel. Alright, let's see if we are able to run this guy. Okay, there's some error. Oh, the server was not started, so I think it should run this time. Yes, it started already. This is cool. So I like to first of all, launch this rocket of ours before I can start with the stuff that I'm trying to start with. So it's not that stable. It is not supposed to be. No, it was too easy, man. The rocket is too overpowered. So I'll retract the gears. We'll change the velocity to something that won't exactly stall it, but won't also crash it. Being on land is better, but I don't want to crash with those mountains, so I'll switch to something which is safer. Cool. This is good. We are not much on velocity, though we are gaining it. So let it be in this particular configuration. We have a lot of fuel, but it's nothing to worry about. If I want to, I can switch to the preview here already. So I'll maybe stop this guy, go back to the code, and maybe we'll try some things out from the start itself. So yeah, let's just print out our current coordinates with respect to this reference frame. Alright, so these are our coordinates, and if I am to loop this, So while true, if I'm to print this, and I'll add a delay because else it will definitely crash. Say a second delay of a second or 2 seconds. Alright, so I'll just resume the flight and I'll rerun this, and we are getting our coordinates every 2 seconds, and you can see that these are changing because, well, we are accelerating on a slope. So if I am to see this, we are basically accelerating on a slope, and that's the reason those coordinates are going to change. So I'll stop that particular implementation. Okay, so cool. That has not stopped. Okay, I'll delete it. This should stop it now. Yeah, so these are some reference frames. I'll like to use some of these. Here we are using the surface velocity reference frame, and we are okay. So this is what I'm supposed to try now. I wanted to see what this drawing thing is actually. Anyways, so I'll run this guy. I'm not sure if I have a connection at the moment. Okay, we do have a connection. I'll stop it, start the server again, go through the 3 initial blocks. Okay, we'll have to restart the kernel here, which will take some time. Yeah, then we can have a look at this. We are very slowly gaining some altitude. Now I don't want to gain altitude rapidly, so I'll just be with the nav ball for a very slow prograde burn, and we'll try to actually do a stability assist thing here while the server is restarting, the kernel is restarting, I'll say. Alright, got a can of Coke by the way in the meantime. Let's switch back to the code. Okay, I'm not even sure if we are getting I'm getting good audio from the stream. I'm not sure of that. Let me check that. Yeah, the audio is good. Cool. I just want to make sure that the desktop audio is not too loud. I actually don't want to hear it at all. This is much lower. Okay, so I'll see what this drawing thing does. Again, run the kernel. Okay, did we get an arrow over here? Let me check if that's an arrow. So if you can see, there's this thing that's protruding out of the rocket. Okay, and I think that's the arrow that we're talking about. Cool. Let's see if this is true. What I'll do is I'll change the arrow a little. So instead of drawing it here, we'll draw it say in this direction, right? And I'll rerun the sky. Now I'll switch to the preview of the rocket and let us see if there's a change. Actually, it's not that easy to determine if there's a change or not. Now, okay, yeah, sure. This is the arrow. Okay, so this is the reference frame arrow, which is very slowly changing. Cool, that's cool. It's pointing prograde only. So what if I am to do a retrograde burn? Will it? Yeah, it is slowly changing because the prograde is following. Cool. Okay, so prograde is now that this particular Osprey aircraft has a lot of control, so it's much easier to control it. Okay, so now I'll switch back to the code and let's see more reference frames then. We use the autopilot over here to turn to certain directions. So yeah, we can do that. We can actually do this in a loop. So I can actually copy the entirety of this and we can do this in a loop. So maybe we can keep on I'll say loitering around a particular point. So I'll restart the kernel once again and stop the server over here. Once that's done, we can do this implementation. Then we activate the autopilot, we set a particular reference frame and we start the autopilot. Cool. So yeah, let's do that over here in the above code block. Once that's done, we'll run a continuous loop and while loop in which we'll just make this guy turn. Okay, let's see how this works. I'm not sure why we are waiting. So waiting is maybe till the particular previous command is executed. Till then we are supposed to wait. So if that happens, then that's cool. Or else after that we can add a time delay as well, so that it can keep doing what it is doing for a while. Cool. So I'll start running this again. I'll resume the flight, start the server, run block 2, which it did, and then run block 3. Okay, so yeah, we are doing some stunts for sure now. It's just that I'm not sure what part of it we are running at the moment, because we are in a loop, so I'm not sure. What I'll do is now I'll first of all stop this guy. I'll add a print here now. So this is a north turn. Cool. And we'll copy this, kinda debugging as to where we are actually moving, right? Okay, so this is a north turn, this is a upturn, and this is a west turn. Sorry. resume the flight, run this block, see if we get some changes. I'm not sure if this is even working because we are not getting any prints yet. So does that mean that we are not doing anything at all? But we seem to be moving. We seem to be going up now, and maybe there's a west turn which is coming. Yeah, this maybe is the west turn. I'm not sure of this. Cool. I'll again switch to this north turn, up turn, and a west turn. Okay, I'll start the server once again. Okay, so we have a north turn now. I'm not sure what ap dot wait is for. Stop this guy, go to the reference, and then there's something about autopilot over here, so I'll check that out. Okay, so autopilot dot wait in Python. Blocks under the western is pointing in the target direction and has the target role. Okay, cool. So that is what I expected it to be. Cool. So what we can instead do is we can make it turn that way. Okay, so I think the reason it's not printing these things is it's because it is turning to those directions, but as soon as that happens, the wait key is not working anymore, so it switches to the next thing, even though that should still do some stuff. But what we'll do is we'll add a 2-second sleep time everywhere so that maybe we can get a print this time, so I can see where we are turning. This is actually completely pointless is what I feel now, this particular part of it at least. Sorry. Okay, we don't have a, okay, that's bad. Switch back to this. I'll have to restart the kernel again. Restart the server. First of all, I'll have to correct this guy. Very high G burn. We almost went to like 15 Gs in this. Megan Kerman is definitely terrified with what we're doing. Those maneuvers, man. Cool. I'll start the server. Run the next block. We are good with it, and then we'll run the final block. So now we are turning north, I guess. We don't have a role. This is us turning upwards. then this is the west turn maybe, and this is the north turn. Okay, this is what I think, but I'm still not sure as to why we are not getting a print over here. I think these should be placed above so that we'll know the turn has started, and I'm afraid we are going to crash soon enough. Okay, okay. Okay. Some changes to the code. Cool, I've run it. It won't overwrite the previous commands, right? So that's not good. Yeah, we have started the afterburner to get some velocity very quickly. We want to reach a higher altitude first. Okay, that's better. Now we can play around. So I'll restart this guy. Actually, I should switch to the code itself. Cool. So we have a server up and running. We'll just go through the documentation of this guy, and then we will move on to the next lesson, which is an orbital flight. And once we are done with the orbital flight, we'll end today's lesson, I'll say. All right, so over here we do some turns as we saw previously, and this is a prograde burn. In a prograde burn, we are deciding the x and z axis to be a 0 and a 1 for the y axis, right? Okay. Okay, understood now. This was actually pretty stupid. We are using a surface velocity reference frame, so actually the target direction should depend on the surface velocity reference frame only. Makes much more sense now. So what we are doing is basically so since we are with respect to the surface velocity as a reference frame, we are basically saying we are giving a command to have our velocity in a particular direction only. Cool. So that's what we are trying to do here then. So if I am to do a retrograde in the same fashion, okay, and if y-axis is my prograde for a particular spacecraft, which is like this, which it would be, I can say do a, I'll say -1 over here, so that should change the direction. Okay. Makes sense. I should actually try that. So now I can make it flip by changing the target direction to a number which is negative, right? Which is, I guess, the case over here, right? So I'll do a retrograde flip, and yeah, this is a surface reference frame, but we want a velocity reference frame instead. So the velocity reference frame is, okay, vessel dot surface underscore velocity underscore reference frame. Yes, so this should technically work, and we are giving it a -1, which means we are going a retrograde turn. Retrograde, this is not a true retrograde, so we'll give it a double asterisk, which will be shown as a single asterisk, just to show that it's not exactly a retrograde turn. It's just basically, I'll comment here. Okay, this is not C, this is Python. Double slash won't work. Basically, ulta flip to -90 on y-axis. Cool. So let's run this, see if our theory as to what we are thinking is true. So I'll resume the flight and run these blocks one after the other. Okay, yes, exactly. We did a very ulta burn, but turns out now we are rotating continuously. Okay, we are not stable anymore. Cool. Okay, so that's what the theory was. It is what it actually also was. Now I'll have to get this guy right and activate stability assist. Cool. So that was okay. Now I'll stop the server here, and maybe we can try something else as well. So what's next? A surface velocity reference frame, orbital body non-rotating reference frame. So this is for rotation then. So we create two reference frames and we print the speed with respect to both of these. Okay, that's okay. Next, what we do is velocity of the vessel related to the surface. Okay, so we should get the surface orbital, or say vessel velocity, and then the surface velocity, and we should get a difference of the two, right? So okay, so we have created two reference frames. No, we have created a hybrid reference frame when we have got the position value and the rotation value. Okay, and the velocity is based on the reference frame. Okay, next is angle of attack. Angle of attack over here is based upon the reference frames, like the direction and the velocity. So we do a dot product of the two, and based on that and some other math, that is like this. So we get a dot product and then we get a magnitude. Okay, so we have a direction and we have the total velocity. Direction will be determined by this guy, and magnitude will basically be the quantity. So if angle is 0, then the dot product, which should be true, Okay, no, so the angle between the vectors, cool, so we don't have any change in vectors. If it is 0, then we'll, and if dot product, okay, we have set the angle to be 0, and if say the dot product is greater than 0, which it would be, then the angle would be the dot product by something or something, and this is the angle of attack basically. Cool. So let's find out the angle of attack in our case. Okay, so this is a finding angle of attack. I can basically copy and paste this entire thing here. I'll restart the server, resume our flight, run the first block. It's not working, so we'll restart the kernel. Okay, once that happens, we'll do it again. Okay, so that's done. Now we'll run the first block, then the second block, and instead of running the third block, which is like a retrograde turn, we'll switch to the fourth block. Before that, I'll have to switch to a Kerbal Space Program preview, which is now happening. Now once I do this, we are getting an angle of attack over here. Okay, the angle of attack has been returned, and are we controlling the angle of attack? Actually, I'm not sure. Like, okay, I'll activate a stability assist system, which it is not working to be. Okay, it's not working. Stability assist is not working. We'll go back to the code, stop this guy. Okay, again move back to the code. Okay, so we engaged an autopilot, which is why the stability assist system is not working, because when the autopilot is on, we are basically following the autopilot. That's okay. Next, what is next? Yeah, landing site. So we are calculating. Okay, so we can add vectors based upon a landing site. So that particular altitude, that particular, I'll say, latitude, longitude, and altitude. Cool. There's much in this code that's happening. I'm a little sleepy at the moment, so yeah, I'm going to paste it, unfortunately. So it's connection. So these are especially useful in terms of docking, etc., and I think I'll be using these a lot in the coming part of the series. Again, switching back to the rocket, I'll start the server, restart the kernel over here. Alright, run this one after the other, and okay, we have a connection in the rocket. We'll resume our flight. we pulled some massive G's here. I'll toggle the mode again. We are very rapidly gaining velocity. I'm pulling more than 15 G's. I'm feeling bad for our pilot here. That's okay. Okay, now we'll switch back to the rocket. Okay. Okay. We'll restart our server. Run some of these guys again. We have a connection, which means we won't be able to control the rocket anymore. So better start with this. Alright. Have we not imported a math as a library here? Okay. It's trying hard to do something. Okay. But there are no arrows. These hard bones are not good for it. So what I'll do is I'll again switch to our code, and I'll not engage the autopilot until and unless necessary. Right. And I'll rerun these blocks. We don't have a connection yet, so we'll restart the kernel. Okay. Okay. We have a connection. I'm sure I imported math as a library. Okay, we did not import sine, cos and pi. Okay, my bad. We'll do that over here. From math, import sine, cos and pi, and we'll run this guy. Sure. So there are two reference frames now, as it seems, and I do not see any drawing whatsoever. I don't see any drawings over here. Alright, I think this is enough for today. I'll stream tomorrow as well. We'll try to be more consistent so that we can do much more in the limited time that we get here.